Hello there, Mr. Sutton here, bringing you the AB Calculus 4-5 Part 2 homework solutions, continuing our discussion of points of inflection and also throwing in the second derivative test.
For this problem, I'm given the first derivative of a function, f prime here. I want to know the coordinates, the x-coordinate of the point of inflection for the graph of f. So for this, I need to figure out where f double prime is changing sign. To do that, I need to take a derivative, but I only need one derivative because they already gave me the first derivative. So just make sure you don't take two derivatives by mistake here. So second derivative then, that's going to be 12x cubed minus 36x squared. And now setting this equal to 0 and solving for some critical values, we can factor out a 12x squared. That leaves me with an x and a minus 3, and all of this equals 0. So this is going to be true at x equals 0, and for this parentheses here, 3. Setting those up on an f double prime number line. Test something from each interval. Let me test out negative 1 over here. Now this x squared is going to make things positive when you plug it in. So really, it's just this x minus 3 that determines the sign, because 12x squared is always going to be positive. So negative 1 minus 3, that's a negative. Now something between 0 and 3, let's try 1. 1 minus 3 is negative. Something bigger than 3, like 4. 4 minus 3 is positive. So I see here that f double prime changes sign at x equals 3 only. So that means f's only point of inflection is going to be at x equals 3, which gives us choice A.
For this problem, they're giving us the first derivative of a function. It's x minus 4e to the negative sign of 2x. And they want to know how many points of inflection the graph of f has. And it's on the interval from 0 to 2 pi. So one way you could figure this out would be to figure out f double prime, graph that out, and see how many times it changes sign. A more direct way to do it, just using the function they've given us, would be to see how many times f prime itself reverses direction, so changes from increasing to decreasing or decreasing to increasing. So what I'm going to do is actually graph this and see where we have these changes in direction. So let me go to Desmos for that. So here I am on Desmos, and to graph this, I'm just going to call it G. It doesn't like primes when you put them in without any other thing to put a prime on. And we've got a G of x equals x minus 4e exponent, and then a negative sign of 2x. And that looks like an interesting looking graph there. Now we want to look at this on the interval from 0 to 2 pi. So I'm going to go to my wrench and change my x values. I'm going to make this go from 0 to, I can write out 2pi for 2 pi. And just to make my life a little easier, I'm going to change the step so that we're going by pi's instead of going by non-pi's. So I'm looking between 0 and 2 pi, seeing how many times I change direction. Here's my graph. Let me just copy and paste that over here so we can look at it. And I change direction, it looks like 1, 2, 3, 4 times. So that's telling me that I have 4 points of inflection on the interval from 0 to 2 pi, which gives us choice B.
For this problem, we've got some twice differentiable function f, and we want to know which properties guarantees f will have a relative min at x equals c. So let's just go through them and see what we can eliminate. First one, f prime of c equals 0. Well, that would be a good start, but it's not enough. For one thing, that could be a max that we just found, or it could be a plateau. Either way, that is not enough by itself to guarantee that this is a min. Next one, f prime is 0 and f double prime is negative. Well, this means we've got a concave up kind of thing going on. We're a smooth turnaround. We're at the top of a frown. So this actually guarantees that we have a max, not a min. So that's a no. This next one is kind of the other way around. Now we have a smooth turnaround with that 0 first derivative, and we're concave up. So we're at the bottom of a cup. This does guarantee that we have a relative min. So this is a good answer. Let's just look at the last one, though. F prime positive before we get to C, and then it's negative after c. So we're basically, our original function's increasing and then decreasing. This is a good way of proving that you have a max, not a min. So that's a no again. So then choice C. On this calculator-free problem. We have the f function given by ln of x over x greater than 0, and its derivative, which we could have found on their own, but they just saved us some time, is given by f prime over here. First task is to write an equation for our line tangent to the graph of f at x equals e squared. So if I'm doing a tangent line, and I don't need to do anything else with it, like approximating or anything crazy like that, I'm just going to use my point slope formula. So y minus y1 equals m times x minus x1. So in this case, applying it to this particular problem, I've got y minus, now the y value I need here is f of the input, f of e squared, the x value. So I'll figure out what that is in a second. For m, that's going to be the slope of f at e squared, so f prime of e squared then. And then x minus x1, that's just x minus the x value they gave us, so x minus e squared. All right, I'm going to go a little further now. Because I know what f does, it takes the ln and divides by the number that you plug in. So this is going to be y minus ln of e squared over e squared. F prime of e squared, just plugging that in here, that's 1 minus ln of e squared over e squared squared. And then finally, we still have x minus e squared. These are all considered constants. You could actually leave your answer in this form and it would be acceptable to a grader, but if you felt the compulsion to simplify it, I just kind of twitch when I see ln of something with an e in there. You can simplify this first thing to y minus, this is just going to be 2 over e squared. And then over here, let's see, ln of e squared is 2, so 1 minus 2 is negative 1 over e to the 4th. And we still have x minus e squared. Doesn't get any simpler than that. For this part of the problem, they want the x-coordinate of the critical point of f, and is it a min, max, or neither, with justification. So if I want critical points for f, I need to figure out where its derivative, f prime, is either 0 or undefined. Let me start by setting this equal to 0. So if I'm trying to zero this thing out, that means I need to zero out the numerator. So I can write 1 minus ln of x equals 0. And if I add ln to the other side and take the e of both sides, or rather raise e to both sides, we end up with x equals, well, just e. So that's going to be a possible critical value. Now, in terms of what makes this undefined, we see that if we plug 0 in for x, that's going to make our derivative dne. However, they said that x had to be greater than 0 anyway, so it couldn't be 0. Also, if we plug in negative numbers, that's going to mess up the ln function. So in general, f prime is non-existing for x less than or equal to 0. So when we write out our f prime number line here, we're going to make sure that we're starting at 0 and not trying to plug in anything that's either 0 or negative. So I have 0 as a firm kind of endpoint here, firm open endpoint, and then I have my critical value of e further along to the right. And now I need to test values in both of these two intervals here. So something between 0 and e that's easy, no pun intended, to plug into f prime. Well, there's a few candidates here. For example, 1 would be pretty easy because the ln of 1 is 0, and that would give us a positive if we plug it in. I actually went with e to the negative 1, just because that's also pretty easy. When you take the ln of this is just negative 1. So we have 1 minus negative 1 is a positive, or just e to the whatever is already a positive. Squaring that just makes it still positive. So positive overall for that interval. And now something bigger than e, well, something that's easy. How about e squared? That would be 1 minus 2, which is a negative in the numerator. Denominator is still going to be positive because e squared squared is a positive. So overall negative result. Now in terms of justification, I see that f prime is changing from positive to negative at x equals e. Therefore, f has a relative maximum at x equals e. For this last problem part, they're telling us the graph of f has exactly one point of inflection, and they want us to find it. So that means we need to figure out where f double prime takes on a value of 0 or is undefined. Means we need to find f double prime in the first place. All right, well, we've got f prime. We just need to take the derivative of f prime. That's going to require the quotient rule here. You could split this up into two different fractions, but you're still going to need the quotient rule for the second one. So let's just set up my box and ribbon right away. I have my numerator, 1 minus ln of x, denominator, x squared, and their derivatives. Derivative of 1 minus ln of x, that's going to be negative 1 over x, or negative, I guess you could write it as x to the negative 1, either way. Over here, x squared becomes 2x. Using my ribbon now to put all this together, and I'm going to simplify as I go here. I've got a negative 1 over x times x squared. That's just negative x. And then just distributing this 2, and that we have a minus going through these here because it's minus uv prime. This is going to be negative 2x. And then minus minus gives us plus 2x ln of x up there. And then finally in the denominator, we've got whatever this thing is squared. So I'll write x to the 4th at some point. Let me just simplify this a little bit more though. Then I'll write x to the 4th. So this is going to be negative 3x plus 2x ln of x upstairs. Downstairs we have x to the 4th. And now let me see where this thing equals 0. At this point, if you wanted to, you could actually cancel an x, one of the x's from here, this x and this x, and maybe make life a tiny bit easier. But if you forgot to do that, that's okay. I'll show you what happens anyway. So we need our numerator to take on a value of 0. And if we factor out, let's see here, we can factor an x out. So there's that x that you could have factored out and canceled earlier. That leaves us with negative 3 plus 2 ln of x inside. So that's going to give us solutions for this of 0, which actually doesn't count because it makes the whole thing undefined. And also if I, let's see, add 3, divide by 2, so I've got 3 halves, and raise e to both sides, e to the 3 halves would be our other solution, our only real solution out of this. In general, we note that the second derivative is going to be undefined if x is either 0, because of the 0 here, or negative because you're plugging negatives into ln. So dne for less than or equal to 0. Again, take this into account when you do your sign analysis. Here's our f double prime line starting at 0, and we have an e to the 3 halves along the way. So now let me go ahead and plug in something between 0 and e to the 3 halves. I could plug in 1, that would be pretty easy. Or I can plug in e, also pretty easy. That goes, I'm going to use my simplified version here. So let's see here. This is going to be, we got negative 3e. We have 2e times, this is just 1. That's negative overall upstairs, positive downstairs. So negative overall. And then something bigger than e to the 3 halves like e squared. So let's see here. This is going to be, ln of e squared is 2. So this would be 4 e squared, and then we have negative 3e squared, so that's positive upstairs, positive downstairs, overall positive. So now that I've done this, I note that f double prime changes signs at x equals 3 halves. So that means that f has a point of inflection at x equals 3 halves, e to the 3 halves rather. On this non-calculator-based free response problem, we're given the function f is k times radical x minus ln of x greater than 0. K is positive, so that's our background here. It's not a whole lot of background. Part A, we want to know f prime of x and f double prime of x. Now the key to doing both of these is recognizing that k is a constant, so we're going to treat it as such. So I'm going to start by rewriting this as f of x equals kx to the 1/2 minus ln of x. That'll make it a little bit easier to do my power rule on the next step here. So f prime then, we're going to have 1/2 k x to the negative 1/2 minus, and you can write this as 1 over x or x to the negative 1. I'm going to go with x to the negative 1 just because that'll make it easier to do the next step. Exponents are always preferable to anything else when you're taking derivatives. So next, for f double prime, we're going to do, let's see, this is going to be negative 1/2 times positive 1/2. That's negative 1/4 kx to the negative 3 halves. And then over here, this is going to be positive 1 x to the negative 2. So there we are, f prime, f double prime. For this problem part, we want to know for what value of k does f have a critical point at x equals 1, and then is that going to be a relative min, max, or neither? with justification. Okay, so let's find k first. For critical points, we basically need to figure out when I plug in 1 to my f prime, at what k value does that all come out to 0? So if I look at my f prime that I created in part A, here it is again. So if I plug 1 into all of this, so 1/2 times k times 1 to the negative 1/2 minus 1 to the negative 1, if I do that, what value of k makes all this come out to 0? And we're only concerned with where we get 0 versus dne, because dne would also give us critical points for the first derivative. But the only place your first derivative is going to be undefined is if you're taking square roots of negatives, which we can't do because they specified x is greater than 0. So this is the only critical values we care about. Now, when you raise 1 to any power, it's still just 1. So this is going to be 1/2 k minus 1. We can add the 1 to the other side. So we've got 1/2 k equals positive 1. Multiplying by 2, we see that k equals 2. All right. Well, we need to figure out now, if I use this k value, do I have a min, max, or neither? And probably the easiest way to do this is just to use the second derivative test. So let me do basically, here's our second derivative from part A. So let me do f double prime of 1 and see if that gives us a positive or a negative. So let's see here. That's going to be negative 1/4 times our k value that we just found, which was 2, times the x value 1 to the negative 3/2, plus 1 to the negative 2. So let's see, 1 to anything is just 1, so this is really negative 1/4 times 2, which is negative 1/2. Over here, 1 to the negative 2 is just 1, so we're adding that. Negative 1/2 plus 1 is positive 1/2. Now, the most important piece is that this is positive. That means we are concave up, so we're at the bottom of a cup, which means that f is going to have a relative min at x equals 1. For this final boss battle part of this problem, we've got our work cut out for us. For a certain value of the constant k, the graph has a point of inflection on the x-axis. We want this value of k. Now, what makes this especially tricky is that they're not telling you the x value of the point of inflection. They are kind of telling you the y value. If it's on the x-axis, then we know the y value of our point of inflection is 0, and that's going to be useful later. But this is definitely a step up from the problems we just had to do. All right, but let's start off. They said we have a point of inflection in general. So that means that f double prime from our previous problem part has to have a value of 0. Now we know that these are the types of critical values we're looking for f double prime rather than places where f double prime is undefined. Because if you look at f double prime, which is this function right here that we had from part A, the only place that's going to be undefined is if you plug in 0 for x or negative, so you're square rooting negatives. But we can't do that because they said right away that x is going to be a positive number. So these are the only critical values we have to consider. And that's enough, believe me. All right, so I'm going to rewrite this a little bit without these negative exponents. I'm going to find this is going to make it easier to isolate some things. Ultimately, I want to know what k is. So let me try to get k by itself and see what happens. So I can rewrite this as negative 1, let's see, k over 4x to the 3/2. And then this one I can rewrite as 1 over x squared. And I'm just going to subtract that to the other side. Now to isolate k, I have to multiply both sides by a negative, which is going to get rid of this negative, and also 4x to the 3/2. So if I have 4x to the 3/2 over x to the 2, subtracting my exponents, that's going to give me, let's see here, I'm going to have an x to the 1/2 downstairs. So 4 over the square root of x then, when all is said and done. This doesn't help us, though. At least it doesn't help us right away, because we don't know what x is. We don't know the x value of our point of inflection. So we're going to need a little bit more information. We're going to need another equation so we can solve a system of equations. And if we figure out what x is, then we can go back here and figure out what k is. So my other equation is going to come from what they said, where they said the point of inflection is on the x-axis. This tells us that whatever x is, with the k value plugged in, we know that it has a value, f of x has a value of 0. If it's on the x-axis, the original function returns 0 as the output. So we can then write k radical x minus ln of x equals 0. Now this looks kind of gnarly, but we do know kind of what k equals. K is 4 over the square root of x. So we can substitute 4 over radical x in for the k up here. So we have 4 over radical x times radical x minus ln of x equals 0. The nice thing about this, it just so happens these radical x's are going to cancel. So you have 4 minus ln of x equals 0. So then I can write 4 equals, if I add this over to the other side, 4 equals the ln of x. And then just solving this, I just raise e to both sides. So we have e to the 4th equals x. Hey, we just figured out what x is. So we're going to plug this e to the 4th back in for the x over here. And now we can figure out what k is. Well, we can write k equals 4 over the square root of e to the 4th, which is fine. It's a constant. We don't have to simplify it. But if you wanted to, you could make this 4 over e squared, and that would be our final answer.